In this video, I'm going to explain about the router switching function. I'm going to use the 7 layers of the OSI reference model to represent how the data from PC1, which is the source IP addresses of 192.168.1.10, route to the PC2 for the destination IP address of 192.168.4.10. I'm also going to explain about how the encapsulation and decapsulation process works. Now, assuming that PC1 is sending a data to PC2, so the data will pass down from the layer 7 to the layer 6 to the layer 5, 4, 3, 2, and 1, and when it reaches through this layer 1 cabling here, it will convert it to the binary bits and pass it to the router 1 interface of FA0/0. When router 1 receives it, you're going to check the MAC address of these incoming frames, and you're going to check the IP addresses of layer 3. The router 1 found out that the destination IP addresses is not dedicated to this router 1. Therefore, the router 1 will going to encapsulate the IP addresses of the destination IP, which is 192.168.4.10, and pass down to the layer 2, informing the layer 2 that in order for you to route to the destination address, which is 192.168.4.10, you have to pass by this router 2 interface. So the encapsulation of this layer 2 here is to determine the next hop MAC address that you're going to send. So it will encapsulate, go down to the layer 1, and it will convert it into the binary bits and pass it to the router 2, and it will arrive here. Now, same thing goes to the router 2, receive the binary bits, decapsulate to check the MAC address of the layer 2, and it will going to check the destination IP address. Router 2 also found that the destination IP address is not dedicated to the router 2. Therefore, router 3 will go into the layer 3 of the router 2 is going to encapsulate the destination IP address and pass down to the layer 2 to inform that in order for these frames to pass to the destination of 192.168.4.10, it have to pass by a device called router 3 MAC address. So it will encapsulate the information of the next hop MAC address of the router 3, and it will convert it into the binary bits, and after that transfer it to the router 3. Now the process go all over again. For the router 3 here, they will have received the layer 2, check the layer 2 MAC address, and then it will check the destination MAC address. Now this round, the router 3 found that the destination MAC address is directly dedicated to its interface of FA0/0, which is the 192.168.4.10. That's why when PC2 receive it, it will going to decapsulate all the frames from layer 1 to layer 7. So this is how the encapsulation and decapsulation process works. Now let's look at the second examples here. For PC1 to send a packet to PC2, the following occurs. PC1 must determine if the destination IPv4 address is on the same network. If it is on the same network, PC1 will obtain the destination MAC address from its RRP cache or use the RRP request. Now, because the destination network is on the different network, PC1 forwards the packets to its default gateway. To determine the MAC address of the default gateway, PC1 checks the RRP table for the IPv4 address of the default gateway and its corresponding MAC address. An RRP request is sent if it is not found. So when PC1 has the MAC address of router R1, it can forward the packet. When R1 receives the Ethernet frames from PC1, the following occurs. Router R1 examines the destination MAC address, which matches the MAC address of the receiving interface, and copies the frame into its buffer. R1 will identify the Ethernet type fields as 0x800, which indicates that the Ethernet frame contains an IPv4 packet in the data portion of the frame. R1 decapsulates the Ethernet frames. Now, because the destination IPv4 address of the packet, which is 192.168.4.10, does not match any of the directly connected networks on router R1, R1 will searches the routing table for a corresponding route. R1's routing table has a route for 192.168.4.0/24 networks. So that's how these routing tables present here. Okay, assuming that the R1 routing table is 192.168.1.0. So because this 192.168.10 is directly connected to this network, and the number of hops is actually 0. And the next hop IP addresses is, you don't have to go through the next hop because the destination IP addresses is directly connected to 192.168.1.0. So in this case, the next hop IP address is directly connected, and the exit interface, which is interface FA0/0, is to reach 192.168.1.0. Okay? Now, if from the R1 perspective, if R1 would like to route the network of 192.168.2.0, how many numbers of hops is required? Now, because R1 is directly connected to 192.168.2.0 here, which is here, 192.168.2.0, okay, so there is no number of hops. The number of hops is 0 because R1 is directly connected to this network, which is 192.168.2.0. So there is no next hop IP addresses, and the exit interface is interface of FA0/1 because the direction is from PC1 send a data to PC2. Okay. Now, if R1 routing tables here would like to send packets to 192.168.3.0, the next hop IP address, next hop, is hop to this interface, which is 192.168.2.2. Okay, that's why you get the answers here, 192.168.2.2. And in order to reach to the network of 192.168.3.0, you need to hop one time to reach to this 192.168.3.0. So therefore, your number of hops here is only 1. Okay? And your exit interface of this router 1 to go to this net of 192.168.30 is through this exit interface of FA0/1. Now, how if router 1 would like to goes to this 192.168.4.0 network here? Okay, so the number of hops will be, number 1, hops to this router one time, and number 2, hop to this router 3 interface, then only to reach to the destination, right? So in this case, the number of hops is 2. Okay, and the next hop IP addresses that for this router 1 to route to the PC2, the next hop, which is to this interface, 192.168.2.2. Okay, and the exit interface of this router 1, which is the door of the exit interface, is connecting to FA0/1. That's why you got the result here. Is that clear? Okay, now we're going to use this another examples here. When the router 1 receives the Ethernet frames from PC1, the following occurs. The route that the router R1 finds to the 192.168.4.0 network has a next hop address of 192.168.2.2 and an exit interface of FA0/1. Now this will require that the IPv4 packet be encapsulated in a new Ethernet frame with the destination MAC address of the IPv4 address of the next hop router, which is 192.168.2.2. Now because the exit interface is on the Ethernet network, R1 must resolve the next hop IPv4 address with a destination MAC address using RRP, assuming it is not in its RRP cache. When R1 has the MAC address for the next hop, the Ethernet frames is forwarded out of the fast Ethernet 0/1 interface of R1.